This video is about medium voltage automatic changeover or interlock system, which becomes necessary when the magnitude of the current or the power to be handled is more than what can be handled at low voltage, such as 400 volt line to line or 230.9 volts line to neutral, which is the phase voltage. Another factor is that, another fact is that when the design current or the design power at low voltage is more than 3,200 amps triple phase with neutral, that is equivalent to a power of 2.2 MVA. So when the design current exceeds 3,200 ampere, and that is the current rating of the highest or the biggest NCCB, that is model case circuit breaker that is really available in the market. So when the design current is more than the current rating of the biggest circuit breaker that is available in the market at low voltage, then the next voltage to be used in the interlock system or the automatic changeover system is the next voltage will be the medium voltage. In two of my videos recently uploaded, namely high tension transmission, that is transmission at high voltage and low current, and also power distribution at medium voltage, I talk about the effect of voltage drop as it could lead to the use of, or as it could make the designer or the engineer to prefer making use of medium voltage such as 11 kV or 33 kV instead of low voltage. Yes, I mentioned it. So today we are talking about the magnitude of the load itself, that is the power rating, the overall power demand, and as well as the current. So if the design current at low voltage is such that the circuit breaker to be used, its current rating is not readily available in the market, then there is no any other option than to move on to the use of the medium voltage, which is 11 kV or 33 kV. We will use an example to illustrate how the changeover system or the interlock system can be done at medium voltage. So, but before we do that, please subscribe to my JK Solutions channel, and you will be hearing more from the channel, especially regarding the medium voltages and other interesting topics. Thank you. Now, moving on with the illustration. The MV interlock system or automatic changeover system comprises three sides: the mains supply side, the emergency power generation side, which is the generator side, and the load side. Here at the main supply side we have the metering system. This is a ammeter capable of reading from 0 to 400 ampere, and then we have the control or the protective devices, which are relays. All these, they are relays. Then we have pilot lamps, and then we have the motorized circuit breaker, which is a vacuum circuit breaker. Vacuum circuit breaker, VCB. Okay, vacuum circuit breaker. So, which is motorized and is at 11 kV. So at 11 kV. 11 kV. Okay. 11 kV. That's why it is written 11 kV panel. Now we come to the generator or emergency side. We have two number 800 kVA generators, diesel generators, and we also have two number 500 kVA diesel generators as well at low voltage. So this is so this is 400 volts line to line, 400 volts line to line. Okay, so and 230 volt line to neutral. So power is generated at low voltage. Now we come to the, from here, the total power being generated is about 2.6 MVA. So which cannot be handled by, the current of 2.6 MVA is about 3,753 ampere. So which cannot be handled by 3,200 ampere triple phase with neutral circuit breaker that is readily available in the market. So because of that, we decide to split the bus bar here into two sections, BS1, BS2, so that the current, the low voltage current, can be managed. With that, we now have the outputs from each bus section, this one and this one, and we step up the output of the generator from 400 volts, which is low volt, to 11 kV. So that's why we are having step up transformer here, step up transformer here. Then we have the medium voltage 11 kV transformer paralleling panel. So we parallel the output of the two transformers. All right. So and the output delivers supply to this section of this 11 kV panel. So the main side of the system, of the changeover system, delivers power to this side. This is the circuit breaker on the main side, and this is the circuit breaker on the emergency power supply side. So here we have the RMU, okay, which the RMUs supply power to the step-down transformer. These are step-down transformers, and eventually the step-down transformers supply power to the feeder pillars. These are feeder pillars. So, and from the feeder pillars, power is supplied to different locations around the feeder pillar areas. Moving on, these are two step-up transformers, and this is the paralleling panel. The paralleling panel, rather, their outputs are parallel, and that's to produce this single line of output. And the fact now is that when there is a mains failure, the generator starts supplying power to the load, and before that one can be done, that is why we have this motorized vacuum circuit breaker interlock. This one closes while the circuit breaker on the mains supply side opens, since there is no power from that side again. And then instead of the loads through the feeder pillar receiving power from the mains, they will now be the loads will be receiving power from this side, which is the generator or the emergency power supply side. Now the summary is this: whenever there is power failure from the mains, a signal is sent to the AMF panel, which in turn signals to the generators to start. The generators start and start supplying power to the loads. So, and when the power is restored from the mains, the panel also sends signal to the AMF panel, and the AMF panel signals to the generators to also shut down. And there is also a changeover from the generator back to the mains supply. Before, normally it used to be the mains supply circuit breaker that will be on. So, and when there is interruption in power, that of the generator will be on, while this one will be off. So, and when the power is restored, the changeover, there will be a changeover from the generator back to the mains supply. And another thing is that, why are we having a medium voltage automatic changeover system? The reason is that the magnitude of the power, and hence the current that needs to be handled, is more than what can be handled by 3200 ampere MCCB circuit breaker that is readily available in the market, and is also the highest that is readily available in the market when we talk about the MCCB, especially at low voltage. So when it is difficult to do the changeover at low voltage, then we make use of medium voltage, which could be 11 kV. In this situation, it is 11 kV, and that is it. Now we come to the abbreviations. MM means metering unit, and that is mains metering unit. MM, which is here, is on the for the main side. Then we have a MG generator metering unit, which is the one that is on the generator side. The NTX means transformer, RMU means ring main unit, X is circuit breaker. All these crosses, they are circuit breakers, and the circuit breakers we are using here inside all the medium voltage circuit breakers, they are all 11 kV circuit breaker, or we call them medium voltage circuit breaker, and they are vacuum circuit breaker because the extinguishing medium is vacuum. That's why it's named vacuum circuit breaker. Then we have a star, then SD means step down, delta, then G1, G2 to G4. They are generators. GP means generator panel. MVI, motorized vacuum circuit breaker interlock. So this is interlock. Interlock. So it's even written here, motorized vacuum circuit breaker interlock. So finally, please, you need to do something for me. Please try and subscribe to my channel and expect more interesting videos. Thanks for watching.